great thing about this room is that I don't really have to do that much introduction to the topic because we have already been talking about the Magellanic Wake and all the different effects that the LMC and SMC system have on the Milky Way underpassage. But I will start, in case you forgot, through coffee, showing the same picture that everyone has been showing to remember what the wake we are talking about. And this wake is also being referred to as the transient response. And in the first identifications, it will also be labeled as the Pisces plume. And it's this typical Chandrasekhar cone that's the direct dynamical friction effect caused by the infall of the XMC system into the halo of the Milky Way. And in case you missed it, is this that small kind of middle ear shaped thing on the left right now. So if we show this same numerical model projected into the entire sky, you will see that it is this overdensity on the lower left corner. And in this study, what we propose to do is to measure what's the density gradient that we see associated with the Magellanic Wake in an observational way to basically get an independent detection of it. So we observed 4 fields. We intended to get a lot more, but a lot of weather constraints only allowed us to get 4 fields. And we observed them with both the dark energy camera, for which we took 25 hours to go very deep. And in the K short, we also observed using the Vista telescope with the VIRCAM instrument to get the K short band. And the reason why we chose to use this specific set of bands is because we wanted to use what's I referred to as the GIKS color color diagram. And this is a diagram that people who work in extragalactic are very used to working with. Because you can easily select, for example, star forming or passive galaxies in this diagram. But what we're interested here is in selecting stars, because we want to map out the density of the stars in the halo. And this is very important because if we go to try to use faint tracers like main sequence turn of stars or giants at distances up to 100 kiloparsecs, we're going to run into a lot of contamination by non-resolved point source-like galaxies. So we wanted to get a very clean sample of stars, which is something you cannot really do if you use, for example, all the dark energy survey bands. And with our clean selection of stars, we set out to work a way to select different tracers. So we chose to use 2 tracers for consistency. We use near-main sequence turn of stars and RGB stars. And the problem here is that the nice thing about this color space is that we can easily select stars, but it's very, very hard to select specific tracers. And we found that there's actually a way in which you can select RGB stars in this space. Working with Camila Navarrete, we found that there's a dependency between the metallicity of the tracer you're looking at and the distance from the center of the what I call the stellar locus. And we also, of course, as I said, selected near-main sequence turn of stars. And this is a much more abundant tracer, but it's also a much fainter tracer. So it tends to suffer from completeness limits. So if we consider a beam between 60 and 100 kiloparsecs, at 100 kiloparsecs, we bump into our 90% completeness limit. So it's a bit of a problematic tracer, but it also allows us to have much higher statistics compared to RGB stars or K giants that were used in all the studies to probe the wake, as has been shown before. But with near-main sequence turn of stars, we got 2,500 stars around, of which around 300 were between the 60 and 100 kiloparsecs of interests for this study. So now with these tracers, we just computed photometric distances. These are not the best, but it's what we can do. And if we're interested in only saying if the star is between 60 and 100 kiloparsecs is enough. And you can see how we can then compare the density between the numerical models. Here I'm using Nico simulation on the right. And the different tracers that we use show the same behavior in a sense. So in here, I'm showing it as a function of right ascension, and that's just because our fields are all aligned in the same declination 0. So you can go from the less dense field on the right to the most dense field at the peak of the overdensity in the center, and you can see that we see a much higher density gradient that all the numerical models predict. And on the left, I'm showing our null hypothesis. So one thing we're very concerned with is, as Vlad mentioned, the junk that we find in the halo. So in a hierarchical formation scenario of the halo, we expect it to be formed entirely out of substructure. So here I took a halo that's made entirely of substructure, which is the Bologan-Johnson simulations. And I took similar slices in width and in different lines of sight and averaged them together to get the 1 sigma deviation. And you can see that we exceed the 1 sigma deviation. And another way in which we can make sure that we're not just looking at substructure in this case is by looking at the radial density profiles. So in the radial density profiles, we should expect to see a given footprint if you're looking for example, a plume or a stream or something like that. We would expect to see a peak at a given distance from the galactic center. And we can see this is mostly not the case. Here, tile 1 is our less dense field, and tile 4 is our most dense one. And you can see that tile 1 tends to decrease. And here we can also see that the hypothesis that is proposed in by numerical models, that the signal is the highest between 60 and 100 kiloparsecs, tend to be true. And the other test we can do in this specific space is check if the shape of the halo is consistent with current fits or radial density profiles. And I think you can do this to better see it. I think these plots are all very, very confusing. You can see what are the residuals between our data and the radial density profiles of the halo. And here I'm subtracting the radial density profile that was used to construct the simulation. So if the simulation was not perturbed, we would just see a 0. And you can see here in gray that the simulation tends to deviate, and this is the effect of the perturbation. And you can see that also our data deviates. However, if we instead utilize a double power law triaxial model, we can get something that's much closer to 0. So our data in this perturbed region of the halo is a lot better explained by a triaxial density profile. However, with the exception of one field, and that's field number 4, which is the one at the peak of the overdensity. So we see that at the peak of the overdensity, you cannot really explain the shapes of the halo either by, for example, a triaxial density profile. We tested all different density profiles from the literature and got none of them to work. So I talked really fast because I'm nervous. So the conclusions are that using the 2 independent tracers, we have obtained a statistically significant detection of the Magellanic wake. And we can see that in the null hypothesis test, we got above a 5 sigma detection. The comparison between numerical models shows that they agree in the position and in the distance that the wake is found. And this is also consistent with previous detection. We found that also the wake can be observed both in line of sight and when comparing different line of sight, so in the right ascension profile as well as in the radial density profile. We found that our measurements of the density differential agree with previous detection. However, they tend to disagree a little bit. For example, Conroy found a density gradient of around 2 for our Lyra stars and a bit less for K giants, but we found up to 3. So it's a lot more than both numerical models, but it is within error bars of the RR Lyra detection. And one thing we can also do is see which one of the models that Nico gave me gives us our best fit. And the best fit is obviously a very massive LMC because we see a very massive wake. And we also found that the shape of the halo cannot really be explained either by a spherical or a triaxial model for the case of the most perturbed field that we observe. So that's all. I'll be happy to answer questions if we have some time.
Thanks, Manuel. Perfect timing. Questions?
Adrian Price-Whalen, Flatiron Institute. Nice talk. So calling it a wake is a very specific thing, right? And I'm not sure we know we know it's an overdensity, but a wake is a very specific type of overdensity. So
Yes.
if you want to see like the convergent flow in kinematics, how far away do you think we are from being able to say something about the relative astrometry of the stars in the wake or something like that?
So there has been a study that related this overdensity. This overdensity has been known for a while now. It was first identified as an SDSS overdense strip. And then Belokurov, I don't remember the year of the paper, but he did a spectroscopic follow-up. And he found that the kinematic footprint of this overdensity in particular matched what the simulations suggested that you would get from a perturbation by the LMC. So I think by this point, it is a bit, the evidence starts to add up, but of course you're gonna need more proper motions to break some of the degeneracies we talked about earlier.
Just a comment, speaking of degeneracies, as I illustrated, increasing the mass of the LMC has the same effect as increasing the anisotropy of the halo, which both make the wakes more pronounced. So in principle, this high mass could be explained also by a lower mass of LMC, but more greater anisotropic halo. So deep kinematics.
Yes, that is a problem that's been bothering me the whole time.
Thanks, Manuel. I'm curious about the nasty and always we hated effect of the selection function. So how concerned are you about how that might be?
You're talking about the RGB stars? Yes, so
I'm talking about the effect of the completeness as a function of distance, because that will affect
yes,
the profile.
given the data that we have, that it is quite deep, particularly our most limited band is decay short, it should in principle allow us to see a G2 star at 100 kiloparsecs. So it is within the limits, particularly for RGB stars, it should not be a problem. All of them are brighter than our limits. And I think that's a good thing about using two tracers, that we get to see if our results change between them. So since we have a bright tracer and a less bright tracer, but that has better statistics, and we found both of them to behave similarly, with the exception of tile 1, which is the one on the right, where you see that we have underdense according to giants, but close to 0 according to numerous single star of stars. But on the most dense fields, we see a consistent behavior amongst the two. So I'm not really that concerned about complex limits issues in this.
Thank you so much, Manuel.
Stuff to fit. I might have to.
Right. Next we have Arpit Arora talking about LMC-driven anisotropic boost in stream superhelio
Hello.
interactions.
Let me just test my pointer. All right, it works. All right, so this is a recent work with Dr. soon-to-be Professor Nico and my advisor Robin Sanderson. So, and this kind of stems down from our conversation on detecting dark matter with LMC. So let's back down for a second and just understand what dark matter is. Well, that's a very hard question, but what we know for sure, or well, hopefully sure, is that dark matter particles can clump together and form substructure that we call these subhalos. And the idea is the number of these subhalos and their properties differ across different dark matter models. For instance, if you look at the CDM picture from one of the simulations, it has a lot more subhalos as compared to SIDM and then the warm dark matter. So a good way to constrain dark matter itself can be to constrain the subhalo mass function and also the properties of these subhalos, because as expected, different dark matter models would produce different concentrations and what some other properties of subhalos as well. So a promising probe to detect these subhalos is to study their interactions with stellar streams. Like we all know, stellar streams are nothing but a group of stars which are on some sort of orbit. And a cool thing about them is that if left unperturbed, they should follow a simple stream track because they were initially in the same phase space volume as a globular cluster or as a dwarf galaxy. But Adrian's work and Anna Panozza's recent work has shown that possibly subhalos can interact with these stellar streams, leading to these morphological structural changes in them. And studying these changes, you can actually constrain properties of these subhalos. Therefore, actually finding these instances of stream subhalo interactions anywhere in the world or anywhere in our universe is a very effective probe of constraining dark matter itself. And given this is a LMC conference and LMC exists within the Milky Way system, I don't know, I think people might fight me on that. The best place to look for these stellar streams definitely is our very own Milky Way. So again, this is an LMC conference, and let's talk about how these MCs or the XMC clouds, as Danny likes to say, comes into this picture. So with Ekta's talk and Eugene's talk, we definitely know that the Milky Way is in disequilibrium. And broadly, you can categorize this disequilibrium in two ways. One of them is caused by the infalling satellite itself, which leads to these density perturbations within the main halo. So it's a Milky Way response to the halo. Secondly, it dislodges the disk of the Milky Way, leading to this disequilibrium in phase space as well, which was Eugene's pretty plot with all the velocity dipoles and velocity vectors. Secondly, in our scenario, the LMC also brings its own population of satellites or subhalos, which are very anisotropically distributed with it, leading to important changes to consider. So the idea is that our stream subhalo interactions are not isotropically distributed anymore because of two reasons. One, that the subhalos aren't isotropically distributed. Second, the perturbations caused in the phase space is very complicated and depends on the position of stream and the overall subhalo population around it. Well, this slide wasn't supposed to be here, so I just skip. Right. So the way people actually look at these stream subhalo encounter rates is by building an analytic model. So the analytic model is as simple as counting the number of subhalos entering some sort of stream length of this, which is this orange bar. So, and some number of subhalos entering this cylinder around the stream length in a way. And what it depends on is majorly two factors. Like I said, the number density and the Gaussian velocity distribution, or just the velocity distribution of subhalos with respect to the stream. And we know under the influence of LMC, these both change. So what's a good way to actually make predictions? I think the way is to find an analog in a cosmological simulation, analog being here, and then just study how streams might interact with subhalos in this cosmologically zoom-in simulation. So what I'm showing here is one of the analogs called M12B from fire simulations. We picked this simulation basically just because of the trajectory or the orbit of the LMC matched with the real LMC, and then the mass ratio or the merger ratio being something like 1:8. Alex will talk a lot more about analogs, I think, in fire galaxies with his velocity dipole talk. The second thing that I want you to see here is this kind of plots the density perturbations caused by the infalling satellite. And you can kind of see that as the LMC falls in, there's this dark matter frictional wake there, and this global response term that happens. So we do see similar density perturbations like we expect in a real Milky Way. Right, so the second thing to look at in this setup is the reflux motion. So in our case, our analog just plots the center of mass of the velocity of central of mass of the Milky Way. And we see almost a change of 60 kilometers per second, which is within what's expected from the real LMC and Milky Way system. The second thing that I show here is this anisotropy in the subhalo population. So what's plotted here is essentially all of the subhalos in my system as a function of time. And the red things are the subhalos that LMC drags on to the main system, causing to these anisotropies. And if you look really carefully, you can kind of see this effect of reflux motion that when the LMC is at its first peri, right about there, there's this certain bulk motion downwards in all of those white points. I'll let it run for another second. Right. So essentially what we want to do is we want to be able to make predictions for observers. That is that if we're looking at the sky in a mole-wide projection of sky coordinates, which sort of quadrants in the sky will have these anisotropic boosts in subhalo stream encounters. And to do that, like I said, we split our sky in 4 parts. Surprise there, but the idea is in our simulation, our LMC is right about here at its first peri, which is sort of like the real LMC, or the trajectory is like the real LMC because it starts somewhere here and then it goes close to the disk. And what we do next is we basically inject about 5,000 stellar streams and also the real streams from Gallstream's package within our simulation and integrate their orbit in this time-dependent potential model constructed with AGMA. And just basically using that simple analytical approach now, but having these anisotropies, we can simply count the encounter rates as a function of a stream's distance, its position, and its other phase-space velocity. So we do that, and then we do a simple statistical analysis just to look at encounter rates as a function of position in the sky, which is marked by these quadrants, and as a function of stream's pericentric distance. So what I want to show here is the solid line, which is the boost in my stream subhalo encounter rates compared to this spherically average profile that people have been traditionally using. And like I said, these boosts are definitely targeted. So in this case, you'd look at quadrant 1, for instance. Quadrant 1 in the outer halo or in the inner halo, that is between 25 to 50 kpc, has sort of a boost, same as quadrant 2. While in the outermost halos, you see these interactions in quadrant 4, where the LMC lives, and then again the northern side of the sky, which again boosted by all those collective response business and Milky Way response. On the right here is a similar plot, but just plotting the boost caused by the LMC subhalos itself. And what I want people to focus on is simply that you should note that this quadrant 2 basically has a less than 10% boost from the LMC subhalos, but the quadrant 2's encounter rates are still pretty high compared to the rest of the things. And obviously, in my case, quadrant 3 is just the boring one where there's nothing going on. I'm going to skip this slide too. And so what we found out for observers were we found these regions within our very own Milky Way where there's a chance to find boosted encounter rates or a higher chance of finding streams that have encountered with subhalos. And surprisingly, this northern part of the sky shows up with the highest amount of boost compared to what's expected from a spherically average property. And then obviously, regions in and around the LMC show up. I'll finish with that and say that all of these can also be interpreted in terms of where to find dwarf satellites.
Right. Thank you so much, Arpit. Questions for Arpit? Cecilia.
Hi, Arpit. Thanks. This is exciting. I wonder, are these subhalos massive enough to cause proper motion misalignments like I mean, maybe not as, of course, large as we see in Chinab, but do you think that if we look for the proper motion misalignments, we should see more in these areas of the sky?
So it's expected, and that's just based on, we didn't do a mass. So there's a lower mass cut, but there's no impulse approximation here or anything that actually says that this quadrant will have the strongest perturbations. But the idea is, compared to isotropically speaking, these quadrants should still have a higher chance. Assuming that all of the subhalo properties are isotropic. So like that means that subhalos that are 10 to the 6 in mass or 10 to the 8 in mass are isotropically distributed in an isolated system.
Okay, great, thanks. This is something that we can look at with the gas streams library, because there's a plot of proper motion misalignment across the sky, and there are some areas where there's.
Awesome, yeah. So what I skipped was we actually made predictions that if these streams existed in our simulation, which ones would have the highest probability of encounters or the highest encounter rates, and those are also marked here. We should definitely look at that.
Yes, great.
More questions? Time for one or two. If not, maybe you can explain the slide that you skipped. You have some time.
Right, so we also looked at how the encounter rates would change depending on stream's own motion. And the TLDR of this plot is, we found that in the northern part of the sky, streams that are in retrograde motions actually have a higher chance of interacting with subhalos. And that's because they are aligned with the bulk motion. While in the streams that are closer to the LMC, the prograde streams have a higher chance of interacting, obviously because they're close to the LMC.
Can also be tested with.
That can also be tested.
We need more streams.
We need more streams. Okay, we can take notes. Okay, thank you so much, Arpit. Next we have Jake Niebauer talking about painting up on perturbations.
Yeah, so I think this follows from Arpit's talk really nicely, because I guess Arpit has this great prediction of an aspherical distribution of subhalos in the Milky Way, using streams to probe that. This talk is going to be about how we might do the inference to try and detect an aspherical subhalo distribution. I'll warn you, it's kind of a methods talk. I apologize, it's a little mathy for this late in the day, but I'm going to put a lot under the rug because it's a short talk. So streams, we heard a good amount about them. This talk will focus on kinematically cold globular cluster streams. So if you have a globular cluster falling into the tidal field of a host galaxy, stars can get plucked from the Lagrange points, and they give you these distinct leading and trailing arms. And they trace orbits, more or less, like Arpit said. But for this talk, we're really going to be thinking about the density structure of streams, less so about their specific orbits, though that all matters. Right, so streams are very sensitive to the smooth distribution of dark matter in the Milky Way. That's been studied extensively. Lately, there's been a lot of focus on sort of the local fluctuations in the potential, and these don't have to be dark matter subhalos. We see asymmetric tails in PAL5, that could be due to the bar. GD1 we just saw in the last talk, possibly subhalos explaining these gaps and bifurcations. We heard about the proper motion misalignment between the stream track and the velocity vector. That's very clearly from the LMC for the OC stream. There's also weird things like JLM has these wiggles and variations in its density that maybe are due to interactions with Sagittarius. There's like a whole bunch of different things that can perturb streams. And I think what I'm trying to get at with this slide is that there's this huge range of forces and scales specifically that are very relevant for modeling streams. The small scales are what we're really interested in for competing dark matter models, but we really need an inference and analysis pipeline that's able to combine many sources of perturbations and sort of paint them all onto the stream so we can try to disentangle basically like who done it, what caused the density variations that we see, and can we get some posterior distribution, something like that. So the idea here is to think about your model for the galaxy as a perturbative expansion, where basically this H0 thing is the entire galaxy, and then this summation is everything else. When I say the entire galaxy, I mean the smooth part, and that everything else are all of the small perturbations, like the subhalos that only act, only give you an addition at very small order in epsilon. That's the idea. So this talk is focusing on measuring the perturbation field using streams, while also allowing for flexibility in that H0 thing, thinking about things like, we want to take into account the LMC, we want to have time dependence in our potential, but we also want to add all of these perturbations. And I want to highlight just how difficult this is if you did it brute force. If you had 100 subhalos and you know all of their orbits and you know the orbit of your stream, that's a lot of givens. If you just want to sample all of the presence and absence combinations, you have a ridiculous number of combinations that you would need to sample over to see. That's a very concerning number. But the subhalos really act as small scale perturbations on the stream. So if you can linearize the effect of the stream on the subhalo, then you've reduced it from having to do these huge sets of nonlinear simulations down to algebraic operations, which are very computationally efficient. A Taylor expansion is really all that I'm getting at. So the method to do this with streams and dynamic simulations, perturbation theory, there's a whole literature on that. And what you do in perturbation theory is you have your equations of motion and you express them as a power series in a perturbation parameter, just expanding it. For this talk, and I'll show some results here for really focusing in on the linear order effect, just trying to extract these Q1, P1 terms that are linear in the perturbation parameter. And these are just derivatives. They're derivatives of the position and velocity with respect to that perturbation parameter. The hard part is getting those derivatives from a complicated simulation. Analytically, there's a lot of work, working out explicitly what these are. But what if you have an LMC and it matters? What if you have a bar and you want to incorporate that as well? So the method for getting those derivatives, and here's where I'm really putting a lot under the rug, but happy to talk about it more another time. It's basically this. You have some unperturbed trajectory that you compute once. That's sort of your orbit in the unperturbed galaxy. So that can include an LMC. I'm using unperturbed in a weird way. Subhalos are the perturbations in this vocabulary. The LMC can be included in that orbit. And then a subhalo goes by, a very happy subhalo. There it is. And the subhalo modifies the H0 trajectory in a particular way that you can calculate just with sort of an integral equation that you can integrate. And what it does is it injects velocity along the orbit. That's sort of what this equation is saying. And then there's these J vectors, which have to do with the tidal field of the H0 part of the galaxy. But basically the story is you just sort of calculate all of these planes by integrating an equation, and it offsets your trajectory to this new one, and you calculated the first order perturbation. There is a procedure to do that. So here's an application of this idea, just going straight to it. So the plots that you're going to see here for the next minute or two are this density contrast. So this is the comparison between a perturbed stream model and a smooth stream model. So perturbed has subhalos, smooth has no subhalos, but there is an LMC and a bar in these simulations. The middle is doing a linear approximation of the top, just with perturbation theory. And you can see the linear order effect due to the subhalos is a pretty good approximation. These subhalos really do act at linear order for certain mass ranges. And the residuals here are quite small at the sub% level, typically. So the real power of this is if you can sample thousands of derivatives, you now have the ability to sort of have 1,000 different knobs that you can tune up and down. So you can continuously deform a stream just by smoothly changing all of these epsilon parameters. So here's a little video that shows doing just that. This is all the same stream. This is a PAL5-like orbit. And I'm just tuning around 1,000 different epsilon parameters to just get a different set of observations. This is very efficient to do once you have the derivatives. So as we just saw, there's a prediction for an aspherical distribution of subhalos. How can we use this for inference? So here's a summary of an inference pipeline. The summary is I'm going to simulate a huge number of impacts. This should really say derivatives, my bad. I'm going to get a lot of derivatives at linear order in the mass. I'm going to fit all of those derivatives, the subhalos acting on the stream, at linear order in the masses. It's just a linear least squares problem. It's very efficient to do. And then I'm going to do some dimensionality reduction, and then I'm going to do some fancy resampling, which I'll talk about in a moment. Getting to the end here. So here's a PAL5 orbit on the sky, and the subhalos that I'm going to inject are the black points. You can tell it's preliminary work because I've kind of put them in the wrong spot based on Arpit's talk. But there's more in the south than the north. That's all I was going for. I got it sort of flip-flopped. It's an easy change to make. So the model here, the base galaxy is going to include disk, halo, LMC, and a bar. The perturbations are just mini spherical NFWs. So here's the sort of mock data. This is the density contrast that you might go out and try to observe. You observe gaps and shifts in a stream and its track. There's 80 subhalo impacts, but the inference pipeline doesn't know that. And then you just try to fit the observations using 4,000 linear order responses. And you get out this sort of surprising thing, which is you can do a very good job, it was surprising to me at least, of reproducing this observed contrast by just taking linear combinations of a bunch of subhalo impacts at linear order. The residuals are ridiculously small. That's 0.01 in the residuals there. So these are sub% level residuals just from 4,000 simulations. Right, so here comes the last part, which is how do we actually do inference with that? Because this picture doesn't tell you what the subhalo distribution is. There's 4,000 subhalos that go into that. The true number of subhalos is only 80. So, but you can do some PCA type analysis, and you'll find that not all of the 4,000 subhalos are important. Some of them matter more. So the goal is to do a PCA in that 4,000 dimensional space, try to find what the most important simulations are, and then resample according to the importance of the simulations. That's sort of the idea. What's really cool about this, though, when you take the principal components, you can ask which simulations have a projection onto that principal component, which are the most important for one principal component. And what you get out are 3 different subhalo impacts, that's what these are, that all look the same. They look very similar. So this is a real degeneracy. You can get very similar qualitative features in this density contrast, but the actual subhalo orbits are different. So that's being captured in this sort of analysis. And a more quantitative illustration of this here, this is the impact time of the subhalos when they hit the stream. The true range is in red, the prior distribution is in gray. And then these black vertical lines, these are the simulations that have very similar sort of contrast shapes. The amplitude of the contrast is very similar for these black lines. You can see that they all sort of fall in the true range. But the real interesting thing is trying to look at the orbital phase of these impacts. So the blue here is the distance from the center of the galaxy of the progenitor's orbit. And you can see that these impacts are sort of preferentially at epicenter. So the statement that I would make is, I can sort of explain one aspect of the data, one aspect of the density contrast by introducing a bunch of simulations that impact the stream at epicenter. You can, that's a real degeneracy in the data. Okay, so finally, the very last slide is next. You resample your simulations according to their importance in describing the variance in the data. And what you can get out of that type of thing is a heat map. So it's a sort of density field of where does the model think the subhalos are, given the most important set of simulations. So you can see it's doing a pretty decent job here of recovering where the impacts actually occurred. The true impact locations are in white. So the take-home message here is, I think that there are ways to do this sort of analysis that doesn't require brute force simulation. One approach could be working at linear order, and you don't have to give up sort of complicated time-dependent models when you work at linear order. It's okay to use simulation sometimes and get that first order response. Turns out it can be helpful sometimes. Thanks.
Thank you so much. Jake, questions?
Thanks for a great talk, Jake. Can you comment a little bit on how you would use this method to distinguish perturbations due to subhalos versus perturbations due to things like the galactic bar or other sources of perturbations to streams?
Right. So subhalos are just one thing that I'm treating at linear order. You can do whatever you want in terms of what you treat at linear order. So you can linearize in the bar's pattern speed, which is something I've tried as well, or its mass. If you change the properties of the galaxy a lot, then the linear order approximation isn't good. So then you need to change that H naught Hamiltonian. So there's a way to sort of sample your base galaxy model while also incorporating everything else at linear order. But you kind of have to make the decision where you draw the line, what goes into H naught versus the perturbations.
More questions?
Thank you, Jake, for the talk. Just for curiosity, how much time does it take to run one of these 4,000 simulations?
Yeah, forgetting the number. It's a matter of like tens of minutes.
Okay.
I have a plot somewhere, but it's deep back there. That I should specify. That's with GPUs and lots of memory.
Oh, okay.
So this is not something for CPU locally.
Mm-hmm.
Yeah, thank you very much, Jake. So for the derivatives currently, are you still calculating them like numerically, or are you able to do it?
Good question. Yeah, so there's a whole aspect of this, which is you can use automatic differentiation and all of these machine learning type advancements. You can use that. I'm not using that anymore because turns out you can exploit Hamilton's equations and work out what those derivatives are explicitly, and that's more efficient. Yeah.
Okay, great. Thank you.
Sure.
Hi, Jake. Nithya Kalibai, University of Virginia. This is a great talk. I am supposed to be working with Anna and Adrian to measure proper motions for PAL5 stream. So no, sorry, it's GD1 stream. See, this is how little I've done on it. But I was wondering for something like the GD1 stream, if you have like predictions for how many gaps you would expect or other features for something like a globular, like a low mass globular cluster.
Yeah, me personally, this is quite new work, so no, not from this type of analysis, but a lot of people have worked on those sort of things. And I think, I don't remember the exact numbers for GD1, but it's like 100 impacts maybe. Adrian, yeah, sorry.
One large impact.
One large impact. This talk is also focusing on the very small scale stuff. Yeah, so I guess one large impact. There you go. Oh, sorry, yeah.
Maybe time for one last question before we change. I have a small question. You can do linear combination because you're in the impulse approximation for subhalos? Is that?
No, it's not the impulse approximation actually. Yeah. So the subhalos impact geometry and its timing all sort of matters here. Yeah.
Just a quick question. How do you guys interpret the different solutions of a PCA? Because it's very tricky and it's not easy to interpret
the similarity of some of them. Yeah, I mean,
values.
I think what was going on with those is you have, it's the derivatives that plot was earlier, but you have the freedom to scale up and down the mass however much you want. So certain subhalo impacts give very similar geometries on the stream. They give rise to similar features. And that's because of all the degeneracies in this problem. And breaking those, you can try to think about it with like velocities and kinematics. Yeah. Thanks.
Thanks, Jake. Now we have Alex Riley talking about velocity dipoles in the halos of fire simulated galaxies.
I'm gonna move around while I can. There we go. Okay, cool. Yeah. Okay. So hi everyone. I'm Alex Riley. I'm a postdoc at Durham University in the UK. And I've worked with a lot of people who are in this room on looking at this idea of the velocity dipoles in like fully cosmological simulations. So I'm going to talk about that today. We've seen this exact GIF before, I think. So this is using, based off of Nico's simulation, n-body simulations of an LMC falling into a Milky Way. The Milky Way gets perturbed in a lot of very interesting ways. The way that I'm particularly focused on is how the inner region moves relative to the outer stuff. And because we are located in the disk of the Milky Way, to us that looks like half the sky is moving towards us and half the sky is moving away from us. This is has been called a reflex motion, or I'm gonna tend to use the term velocity dipole going forward in this talk, but this is the idea. So this has been, sort of studied in these n-body models, and then there's also an observed dipole in distant halo velocities. So this was done by two groups sort of at around the same time, one by Pearson Peñarubia, the other led by Dennis Urkel. And the general idea is that it is true that if you look in the northern hemisphere versus the southern hemisphere, this is the Urkel plot, there's a shift on the order of 30 to 40 kilometers per second between the two in sort of mean GSR velocity. And then the Pearson Peñarubia sample does kind of the same idea, but they fit for the full, they try for the location of the dipole along the sky as well. And they also incorporate proper motions in their analysis as well. But basically, two independent groups finding more or less the same idea of this 30 to 40 kilometer per second dipole signal. But all this was done and it kind of interpreted with antibody models, but we know that stellar halos are comprised of substructure. This is not unique to Lambda CDM, but it is a nice thing that comes out of it. So this is a visualization from the Bullock and Johnston suites where they pepper individual dwarf galaxies to form a stellar halo that's kind of comprised of substructure. And the idea is, could this substructure be influencing the measurement of the velocity dipole? Could we, in a scenario where there is no, basically our velocity dipoles unique to Milky Way LMC interactions, or could this structure end up looking like a dipole, basically? So that's what we're poking around at. So to do this, we use the fire simulations. So fire's feedback in realistic environments, and particularly we used a suite called Latte, which are Zoom simulations of Milky Way mass hosts. Fire, there's a lot of things you could say about fire, but for me and for the purposes of this work, these simulations track structure and galaxy formation in a fully cosmological context. I think at one point I used to know which thing was the LMC analog here. I think it's this guy, but I might be wrong. basically, so we use fire as kind of the basis for all of this. Yeah, okay. So really quickly, kind of set the baseline, we wanted to look at an LMC-like interaction in fire to see if we can recover the expected dipole signal in the simulation. So if you rewind one of these halos, M12F, back to a redshift of about 0.25, this is just the stellar density. There's your LMC located slightly below the disk. And if you apply the same types of algorithms, essentially the same algorithm as Pearson and Penn-Urrutia do to the Milky Way halo, you get a dipole measurement that looks like this. So as a function of distance, we're looking at what the dipole measurement is. For these kind of aquamarine contours, this is looking at bin shells of a thickness of 5 kiloparsecs. And then the yellowish curve that I call cumulative here uses all stars that are beyond a certain distance. So for the value at 100 kpc, I'm using all star particles that are 100 kpc or further to calculate that property. So you kind of get a nice radial profile that increases until you hit some limiting dipole value. This is where the term impulse approximation has been thrown around earlier. This is kind of where that starts to work fairly well. And the really nice thing is that this sort of V-limiting dipole number in this simulation, at least, happens to just about work out to give you the mass ratio of the LMC and the Milky Way. It didn't need to go this way, but we were very thrilled that this was the case. So next, we took a look at tracking this same interaction, but with time. So on the left there, that's just the orbit of the LMC analog. So it has a pericenter of around it's just slightly below 50 kpc. And in terms of the dipole signal that you measure, so this is something like that limiting dipole that I was showing earlier. It's sort of there's kind of noise before this, and then peaks right around pericenter, lives for about 0.2 gigayears, and then drops back down to what was happening before. So this is roughly how long this type of signal can last, at least relative to sort of the kind of static background. And then we also looked at the relative alignment of the dipole signal relative to the position of the LMC at every single snapshot. So kind of beforehand, doesn't really matter. It's sort of random. But once this dipole signal sort of increases, the direction of the dipole motion sort of starts tracking behind the LMC by 90 degrees, and that's about what you'd expect for kind of a very simple two-body interaction if you're in the perspective of the Milky Way, which is where we're doing all these calculations. So all this is like honestly really good news. Tracking the dipole along the sky, this is getting exactly what that plot on the right was showing earlier. So this is not the dipole, but the position of the LMC as a function of time, where 0 is the pericenter snapshot. And then if we plot the actual location on sky of these things, it gets a little funky. But if you interpret it as, okay, before the LMC falls in, the halo can be doing whatever it's doing. So it's not necessarily a bad thing that's misaligned. But then starting around the pericenter snapshot, and then definitely afterwards, it continues to kind of swing by essentially trailing the orbit of where the LMC is, which actually agrees really nicely with what Pearson and Penn-Urrutia find, where the position of the dipole along the sky in the real Milky Way is where the LMC used to be. So all this is like roughly painting a really nice story. We're all feeling very good. Now I'm going to give you a nice dose of cold water here. So the original point, the motivation I was describing earlier. So if you take a a fire halo at redshift 0 that has had an incredibly quiet merger history, does not have an LMC analog. And so that's the same kind of stellar distribution here. So you can see that I'm not lying. If you do the same type of analysis, you get a plot that looks like this. So in the binned shells, we're seeing the effect of individual substructures. Importantly, so I'm removing anything that we would call kind of a bound substructure or a dwarf when I'm doing this calculation. I'm not removing, in this plot, I'm not removing all the streams. We can get into an argument, do we know where all the streams are? I would say no. So I think this is a fair representation of what's going on in the real Milky Way or how we're treating it. But then, so this is actually the plot that motivated doing the cumulative version of this. So you can make the argument, okay, all these individual, you might be seeing individual spikes here, but then if you kind of average over large sections of the halo, these individual dipole signals might cancel out. And you sort of see that there. So over here, where there's like these large spikes in these smaller, thinner radial shells, if you look at a larger swath of the halo all at once, the signals kind of cancel out. There's still this floor of like 10 kilometers per second that you really can't go below. So if no one's claiming this to measure this in the Milky Way, but if you're ever measuring something below 10 kilometers per second, just like don't trust it whatsoever. So that's one idea. And then we also wanted to poke a little bit at what the effect of observational errors are. So it's nice to be in star particle land or simulation land where we know the exact positions and velocities of all these things. But if you just give some sort of jitter in distance and velocity and proper motion, this is something like a wonderful, perfect, clean sample of RGBs at each star particle. You get this kind of interesting, behavior where, so the dashed line on the right is, on the left, sorry, is the not perturbed version. And then the shaded bands are bootstrapping over assigning errors to each of the star particles. And so you can get disagreements where the dipole that you should be measuring isn't exactly the dipole that's coming out. And kind of more crucially to me, I think, how well we can infer, at all of these different distances and different methods of calculating the dipole. We never really do a very good job once you apply errors of getting the direction correct. So this is, I was actually like kind of surprised at that plot. So yeah, so basically I would apply a fair amount of caution to, I think overall, if you're considering the whole halo at once, as people have been doing sort of up to this point, things look okay. And then maybe take directions with a grain of salt. Of course, last Monday, this paper comes out on Archive, run by the same Peterson and Peña-Rubio group. It's a PhD student working with them who led the analysis, where they break up things into radial bins. And then sort of the focus of the paper is they see this increase, which is what we'd expect from the n-body simulations. But we also saw that in the isolated, totally quiet no LMC case in fire earlier as well. And then this is kind of a useful plot for me. They put a whole bunch of different n-body models on the same plot. So you can see there's a lot of variation in terms of the predictions for all these things. But again, we don't know if we're measuring the right direction really at all. So the substructure really seems to affect that a lot. These are the people who fund me, now they can reimburse me. And I'll just leave my summary up here. Basically, actual cosmologically motivated halos are very messy, and that can impact what we infer about the Milky Way halo or any of these other things. Yeah, thanks.
Thank you for the bad news, Alex.
I don't know. I have very mixed feelings about this going forward, but yeah.
You have time for one
Screwed up the
question.
density, now we screwed up the velocity as well.
You have time for one question. Somebody.
Is there like an intuitive reason why line of sight distance errors cause the like direction to have such a large bias? And the bias seems to be in one direction also. Like why?
So importantly, I'm not just doing distances. I'm also doing velocities. So line of sight and proper motions too. I haven't decomposed that at all. Yes. One thing I will say is that having brighter tracers helps a lot more than having like ones that have very, very fine errors on all these things. So I made the same plot for RLI, for example, and it looks a lot better with the RGBs. So that helps.
Do you think we can do something about to get the actual measurement of the direction, or what are your thoughts about that? How will it improve? What data we need? What methods?
Let's write the paper and find out.
Okay. Let's thanks Alex again. We have working. Because
disappear.
okay.
Here. Right.
Oh, deposit.
Why is that? Because that.
Somebody that work with Mac.
Sorry.
No present. What is the opposite? How do you
There to the top right. The arrow right next to that. Right. All the way to I'm getting there.
Awesome.
Why do I have to sit them all in?
All right. So next we have.
Right.
Yeah. Next we should have Isabel Santos talking about the impact of the LMC and its satellites on the Milky Way halo.
Okay. Yeah, so hi everyone, my name is Isabel Santos. I'm a postdoc in Durham. And today, well, first of all, thank you to the organizers for the opportunity of being here. And today I'd like to talk about the LMC, but in a more cosmological context and specifically within the predictions of the cold dark matter model. So in CDM, we know that structure formation happens hierarchically, and this reflects in some fundamental predictions. One is that there are more small halos than large ones. And another one is that there's self-similar abundance of substructure around halos, which just means that halos of any mass are surrounded by lower mass ones. And this can be expressed with a halo mass function and a subhalo mass function, respectively, that would rise very steeply, like this black line here. When we compare this steep halo mass function with the observed galaxy luminosity function, which is much shallower, shown here with the stars, we can see very fast that not all halos can form a galaxy. So galaxy formation becomes increasingly inefficient towards decreasing halo masses. And the thing is that we don't really understand how this decline in galaxy formation efficiency happens. We don't know how steep it is, what's the scatter at a fixed stellar mass. And we don't know if there is a threshold halo mass below which no galaxies can form. So within this cosmological perspective, the LMC stands out as a very interesting object. So one reason is because it's the most massive satellite of the Milky Way, and objects like this are not super common in CDM. And another reason why it's interesting is because CDM tells us that it should have its own subhalo population and its own satellites. And because it's so massive, we would expect that some of those subhalos have a luminous component to them. And also because the LMC today is a satellite of the Milky Way, we would be talking about this concept of satellites of satellites. So this means that if we could disentangle which Milky Way satellites actually came with the LMC, then this would be one way of constraining the nature of dark matter, but also of understanding better the processes for galaxy formation in small halos, which arguably are the most important questions to answer in small scale cosmology. And another reason why the LMC is interesting is because it is today at a very particular moment in its orbit. So we know that it is at a very close distance of 50 kiloparsec and at first infall onto the Milky Way. And I will later discuss how this fact is useful to infer satellite association, but also to inform on the Milky Way's gravitational potential. So a couple of years ago, we carried out a study to put the LMC in a cosmological context, and we used the Apostle cosmological hydrodynamical simulations. These are local group environments. That means that they have 2 massive primaries, and we have 12 volumes, which means we have 24 primaries to study. So the first thing was to identify LMC analogs, and we did this following 2 main criteria, so mass and kinematic stage. So we first selected the most massive satellites that we could find around the Apostle primaries with stellar masses around 3 × 10⁹, which is the mass of the observed LMC. And then out of those, we're going to take only those with recent first pericenters. As you would expect from the nature of hierarchical buildup, most of these massive satellites presented recent infalls and eccentric orbits. And this had been shown before with in previous work. But what was different to previous work was the frequency of these massive satellites. So we found that 14 out of our 24 primaries hosted satellite as massive as the LMC. And this was, this is like 58%. And this was larger than what had been claimed in previous work that said something like 27% at most, and therefore claimed that the LMC was kind of like a rare object around the Milky Way. So this motivated us to think that perhaps the reason why we were finding this increased frequency had to do with the fact that we were studying local group environments. So we went to the big, large dark matter only volume from which the Apostle zooms had been selected. And we identified all the Milky Way mass halos. This plot here is showing the subhalo mass function around these Milky Ways, but separated in groups. So around the Milky Ways that are isolated, which would be the black line, and around Milky Ways that are in pairs, which would be the orange and the blue lines. And we found that indeed there was an increased frequency of LMC mass subhalos around the Milky Ways that were in pairs in binary environments, like a factor of 2 more of them. So this is interesting because it shifts a little bit how we perceive the presence of the LMC in our particular environment. So it wouldn't be a rare occurrence, but rather something we expect within. The LMC would be an expected galaxy within our local group. So going back to the LMC analogs, sorry, we indeed they did come with their own satellite population. Apostle predicted between 1 and 3 satellites per LMC with masses above 10⁵ in stellar mass, which is our mass resolution limit. And of course, because it is a small number, this just means that the contribution of mass that the LMC's accretion onto the Milky Way, the impact is not very large. It's the 10% that comes from the mass of the LMC itself, but not from adding in the mass of the satellites. We can look at the radial distribution of these satellites. So here in orange, I'm showing the radial distribution of satellites around the Milky Way primaries that contain an LMC. And in cyan is the distribution of satellites around all the 24 primaries. And we'll find that the orange distribution is more concentrated. So this we understand because we have the LMC and their satellites at first pericenter, and they are contributing to more satellites in the inner regions. What's interesting is that the Milky Way data was shown with the dashed line follows this orange line. So we can explain the Milky Way data due to this transient event of the LMC at first infall. But understanding that as the LMC moves away in its orbit, this distribution will become much more uniform. And this is also interesting because it helps explain results from SAGA, who find in the Milky Way survey of, the survey of external Milky Way galaxies, where they find also in general much more uniform distributions. So I said before that it would be interesting to disentangle which Milky Way satellites come with the LMC. And the first obvious thing to look at would be the positions in the sky of these satellites. So in this sky projection, I have the position of the LMC in galactocentric coordinates here with a star, and the gray line is the orbital plane of the LMC. So we can overplot the simulated LMC satellites in the same reference frame, where I've highlighted the satellites that are associated to the LMC with big symbols. And what we see is that they, at first pericenter, they're tracing the leading and the trailing arm of the orbital plane, as you would expect, but they are extended, they're quite extended in their distribution. So if I add on top the Milky Way satellites, there are many that follow the same parameter space. So looking at the positions alone is not very constraining to separate satellites that came with the LMC. And a similar thing happens when we look at angular momentum. So many, the LMC satellites show orbital poles with similar directions to that of the LMC, but with enough dispersion to accommodate too many Milky Way satellites. However, when we look at the relative 3D distance and 3D velocity or radial distance of the satellite with respect to the LMC, then we find that it's very constraining. So what we find is that the LMC satellites remain quite bound at first pericenter to their LMC. And this is presumably because there hasn't been enough time for Milky Way tides to disperse the original orbits. And what's more is that in this case now, there are very few Milky Way satellites that share the same parameter space. So we combined these different diagnostics to give probabilities to the Milky Way satellites as how associated to the LMC they are. And we found that these 7 galaxies in red have a very high probability of being associated to the LMC. And this list just adds or constrains further lists from previous works that used independent methods like dark matter only simulations or integrating orbits within different potentials. But I think there's agreement, quite like consensus among these for these 7 objects. So I mentioned as well at the beginning that the LMC can inform on the Milky Way's gravitational potential. So here on the left panel, I'm showing with lines the escape velocity profiles of the primary halos that contain an LMC. And with stars, I'm showing the 3D velocities of our LMC analogs. And what we can see is that the velocity of the LMC at first pericenter is very close to that of to the escape velocity at that radius. So and we find for a pulsar a mean ratio velocities of 0.9. So we can use this prediction of a pulsar and combine it with the observed 3D velocity of the LMC, which we know is 320 kilometers per second, and infer that the escape velocity of the Milky Way at 50 kiloparsecs should be something like 365 kilometers per second. And now we can look at different Milky Way models, and I compiled a few from the literature and see how this compares. So it seems like our result would be favor the model of Garavito Camargo 2019, which is the black line, who used a mass for the Milky Way of 1.2 times 10 to the 12. So the LMC is also useful to constrain the Milky Way's gravitational potential at a radial distance at which we don't really have many other tracers. And finally, I'd like to talk about the idea of galaxy formation in very small halos. So I mentioned that a pulsar predicted between 1 and 3 satellites per LMC, but if we had used any other galaxy formation model, the prediction would have been different. So what is the real number of satellites expected around the LMC? Well, this will depend on how we populate small halos. And this is essentially the same as asking, what is the stellar mass halo mass relation in the low mass end? So There's no consensus yet on this, and I illustrate this with this figure, which shows the stellar mass, halo mass relation for simulated dwarfs from different simulations using different models and different resolutions. Where on the left hand, I've gathered dwarfs that follow a relation that is quite shallow, like a power law. And on the right, I put other simulations, other dwarfs that follow a relation that's much more steep and has a cutoff at low halo masses. And this is the behavior that you would expect in models where galaxy formation can only proceed in halos that exceed the hydrogen cooling limit. And well, it's interesting that these two shapes kind of describe well results from very different simulations. But the idea is that these two relations have very different implications. In the case of the power law, very small subhalos can contain, very small halos can contain a galaxy, while in the cutoff case, very small halos cannot form galaxies. So this would just, it's expected that these two relations will give you a very different number of satellites around primaries. So we explored this with a very simple analytical model where we just sampled the steep CDM subhalo mass function to get subhalo masses. And then we populated these with stellar masses according to the stellar mass halo mass relation. And this gave us satellite stellar mass functions. And here are some results of our model applied to Milky Way primaries and to LMC primaries. And just by looking at the different curves, the red and blue curves, we can see that the power law in the cutoff case predict vastly different numbers of ultrafaints. If we focus on the LMC case, we would be talking about 10 satellites versus 150. So I'm particularly excited for surveys that are looking for dwarfs in the field and searching for satellites around them because they'll have the power to constrain the low mass end of the stellar mass halo mass relation. And yeah, I'll just leave you with my summary. The LMC is a unique object that tests CDM to learn about the Milky Way halo mass and to constrain the low mass end of the galaxy halo connection. And also it's crucial in order to understand different features from the Milky Way satellite population. Thank you.
Thanks, Isabel. Questions?
Hi, Isabel. Thank you for that really nice talk. I had a clarifying question about the plot where you showed the radial profiles for the hosts that do and don't have an LMC. So I think you said that the LMCs are expected to bring in 2 ± 1 satellite. And then when you showed the radial distributions, yeah, here on the right side, what's the total population you're working with? Because to me, I don't know, I think I'm just confused why there's such a big gap because 2 ± 1 additional satellites doesn't seem like it would cause that big of a change.
Yeah. So here I'm only looking at galaxies with high stellar masses.
Okay.
So 2 make a difference or 3. But yeah, and also these are normalized, right? So I guess the shapes can be a bit confusing.
Okay, yeah, thank you.
One more question when we change. Yeah.
Your selection criteria, did it include the fact that these LMC analogs are on the first passage or not?
No, we didn't care about them being in the first passage. We just wanted them to have recent pericenters, and then we looked at them at first pericenter.
Because it would be interesting to see is there any difference between the first
and the second. Yeah, I did not look at successive pericenters. Yeah.
Thank you so much, Isabel.
Yeah, thanks.
Okay, next we have Vedant Chandra talking about shakes, wakes, and streams, the XMC influence 200 kiloparsecs and beyond.
Great. Okay, thank you so much. Thanks to the organizers. It's a real privilege to be here and meet so many people in person for the first time. So I'm Vedant Chandra. I'm a graduate student at Harvard, and I've been spending most of my time thinking about the outer halo, the most distant outskirts of the Milky Way, where of course the clouds play a very outsized influence. And one of the recurring themes we've been hearing at this conference is we need kinematics. We need to find luminous tracers and get kinematics for them. And so for my PhD, that's exactly what we've been doing. We've been trying to build a spectroscopic data set of stars beyond 50 kiloparsecs, going all the way out to 150 kiloparsecs. And for this, we want to use red giant stars. And that's because unlike RR Lyrae or BHB stars, red giants are very luminous on the CMD. And so even at these very large distances, they have precise proper motions. And you can get metallicities for them, you can get abundances for them. And so that makes them really ideal tracers to start doing these kinematic studies. However, a problem has been that the map of spectroscopically confirmed red giants at these distances for the longest time has looked like this. There's a gigantic hole in the south because you haven't had southern spectroscopic surveys filling that in. And so for the past 2 years, I've been having a lot of fun running my own mini spectroscopic survey with the Magellan telescope, filling in these gaps with this new selection of ours to try and finally fill out this region and get spectroscopically confirmed giants going out to 150 kiloparsecs in the southern hemisphere. And there's a lot of science we want to do with this data set, but naturally, once you have these stars in the south, one of the first questions you want to ask is, what does the influence of the clouds look like in the southern hemisphere? And so I promised you shakes, wakes, and streams. I'm going to spend most of my time telling you about the stream part of this. And that's the Magellanic Stream, which of course needs no introduction over here. There's this beautiful H1 map from David. The recurring mystery with this stream has been the absence of a stellar component along the entire stream. We've seen stars, but for decades, people have searched for a bona fide stellar component all along the stream, and we haven't been able to find one. And the explanation that's been given, partially due to simulations that were run by Gertina Bestla and others, is that perhaps those stars and the stream itself just go too far away. They stretch out to 100 kiloparsecs and beyond, and so those stars have been inaccessible to previous surveys. Well, we now have a spectroscopic survey of the southern region of the sky. And so one of the first things we wanted to do was to see if we could find such a stellar counterpart in our data set. And the way we go about this goes all the way back to kind of first semester of undergrad physics, which is angular momentum. And so we know that the clouds are coming in on these very energetic orbits. And so they have these distinct angular momenta that any stars that were stripped off the clouds should also share. And so when you plot our spectroscopic data set in this angular momentum space, we found that you actually do see this very prominent tail of stars that have very extreme angular momenta that match the clouds. And so this was really exciting, but on its own, of course, this isn't a smoking gun. This just tells you that you have some stars that seem to be moving in a manner that's similarly extreme to the clouds. And so we performed 2 more tests. We performed 2 more experiments. We take these kinematically selected stars and we turn back the clock. We rewind them back in a potential that, thanks to a lot of help from Ekta, includes the influence of the clouds. And it turns out that these stars not only have orbits that match those of the clouds, but some of these stars actually become bound to the clouds as you rewind them back in time, analogous to what Ekta was showing with some of the satellite galaxies of the LMC. And so that's very tantalizing dynamical evidence that these clouds are consistent with being chucked out from the, that these stars are being consistent with being chucked out from the clouds as they fell in. And the second piece of evidence is this kind of abundance plane that we get from our spectroscopic data set. We learned on Monday about how stars that are born in smaller dwarf galaxies tend to live lower down and to the left in plots like this, where you plot alpha versus iron. And we find that indeed our stars are consistent in terms of chemical abundances with stars that we currently find in the clouds. And so when you put all of this together, from our unbiased spectroscopic survey of the southern hemisphere, we find a population of stars that move in an extreme manner. And when you plot them on the sky, they lie coincident with the gaseous Magellanic Stream. They correspond with that stream in radial velocities. And it turns out that in distances, they actually do a pretty good job of matching predictions that Gertina's simulations made 10, 12 years ago. Chiefly the fact that the stars do in fact go much further out, from 60 to 120 kiloparsecs. And this perhaps explains why they haven't been seen before. And so I'm really excited about the prospects for what this now Magellanic stellar stream can do to constrain not only the source and properties of the stream itself, because stars have some properties that gas doesn't. chiefly you now have their motions on the sky through proper motions and also distances. And so I'm hopeful that as we find more stars over here, we'll be able to constrain much more about not only the stream, but also the past interaction history of the clouds. And there's something really interesting to be said over there, which is the fact that our stars don't seem to be chemically homogeneous. They actually have kind of a bimodal distribution in chemistry, where some are metal rich and some are metal poor. Some look like they might have come from the LMC. Some look like they might have come from the SMC or even the outskirts of the SMC. And so if you're running a simulation of the interaction between the clouds, not only do you have to produce stars that produce a stream like this, but you also have this added constraint that perhaps you need stars coming not only from the LMC, but also from the SMC. And so I'm just trying to say here that the abundances of these stars can actually tell you not only where the stars should be, but also from where the stars came from in the clouds themselves. And so I think there's a lot more work to be done here in terms of finding more stars. This is kind of the streams aspect of my talk. In my last few minutes, I just wanted to go back to the shakes and wakes, right? So again, this is the kind of stuff that we've seen recently with Alex's talk, for example. These are simulations run by Nico of the entire halo, again, in galactocentric coordinates. The clouds are over here. And you have this prediction that you'll have the overall shake or reflex motion or velocity dipole. That's this overall structure of stars in the south seeming to move towards us. And then you also have this wake signature. What I'm showing you here is not density, it's the mean radial velocity. And you can make similar plots in proper motions, and there's all these kinds of signatures that you'll be able to find in this space. Now, this is all work from last week. This is why it's all work in progress. We'll hopefully have a lot more on this. But currently, our data set, because we now have this all-sky data from 50 to 150 kiloparsecs, covering that gap in the south as well, it looks like this. And so if Dennis Urkel is watching, this plot is for you. It's inspired a lot by some of the work you've been doing. But as you can see, there's some really tantalizing similarities between our data set and these simulations from Nico. Also some differences that are potentially very interesting. And again, all I'm showing you here is one component of the velocity along the radial direction. As I said, these giants are luminous. They have pretty decent proper motions as well. So it's going to be really interesting to see what we can tease out from maps like these, not only in line of sight velocities, but also proper motions. And so I'll flash my conclusions, chiefly the discovery of the Magellanic stellar stream, and the fact that I think these galactic outskirts are finally coming into focus in terms of their kinematics and in terms of their distribution in distance. So I really appreciate your time, and I'm happy to take questions.
Thank you so much, Vedant. Lots of questions.
Thanks so much, Vedant. I'm just curious about your last slide. I know you said it's work in progress. What fraction of the stars in that right panel are Sagittarius, and are any of them Sagittarius? Yeah.
That's a great question. So an important part of all this is trying to peel apart and remove substructures, because these predictions are on kind of a halo without substructure. So here Sagittarius has been removed from our data set before I make a plot like this. We remove Sagittarius using angular momenta, and also on those regions of sky, we're careful to remove stars that have radial velocities that are similar to Sagittarius. For example, the Magellanic stellar stream I showed you would also bias a plot like this. And so we remove those stars as well. Yeah.
Thanks for the awesome talk. I have a question about your comparison with the Besla models. It looks like your stream population agrees with one model versus the other. And so I wonder if you're planning to use future observations to fill out this plot and be able to distinguish between these different simulations, or if you've thought about that.
Yes, definitely. So first on the observational side, with our survey, we're filling this space a little bit more with some more stars. I'm really hopeful with SDSS-5. That's another way we'll start. One of the cartons in SDSS-5 is something we put in, which is very distant luminous red giants. And so hopefully as SDSS-5 fills that region of sky, you'll get more stars. Eventually, you'll also want like fainter surveys to get RLIRE and things like that to get very solid distances. On the modeling side, 100%. So the reason there's two models here is I believe one of these models reproduces the kinematics of the gas stream very well. The other one reproduces the kinematics of the clouds. And so one thing that I raised in one of our little group discussions today is that's exactly what I would like to advocate for future people who simulate this to do, which is now not only should you match the kinematics of the gas stream and the clouds, but also the kinematics and distances of the stars. Yeah.
Hi, still here, still on this side. Thank you. So the talk was great. I was just wondering if you can quantify what you mean by luminous giants and faint giants that you just mentioned. I think you're talking about red giant branch stars, probably not too close to the tape or somewhere halfway, not down to the red clump. So yeah.
Exactly. Yeah. So I don't think I have an actual CMD in my bonus slides, but I'm essentially talking about K giants mostly. And so these are about 1.5 magnitudes to 2 magnitudes brighter than RR Lyrae. And in terms of observed magnitudes, we're talking about between 16.5 to 17.5 in G band in Gaia, for example. So these giant, to put that in luminosity terms, at about 17.6 in Gaia G, you're already at 120 kiloparsecs with these luminous giants. Yeah. But they're not M giants because those get much cooler and much more luminous, but then you have all kinds of other issues with them. They have these deep absorption troughs, which makes it difficult to get metallicity and things like that. So this is a sweet spot.
Yeah, so finding this stellar stream is awesome. So congrats for finding this. People have been looking for a while. One thing I didn't follow, you said the stars and the gas kind of follow each other. Looking at the map there does seem to be an offset. Is there something we learned from that?
Yeah, definitely. And actually, while I was digging into this, I was reading most of your papers, which is, first of all, what I'm plotting here is the H1 gas. But of course, the ionized component of the gas stream does extend further out. So that's one aspect of that. The second aspect is, you raise a very good point, which is, yes, there is one population that follows the gas that also happens to be the metal-rich population. These are the red stars. The metal-poor stars seem to be more offset. And so with no real simulation-based evidence, the speculation we put in the paper is perhaps this red, metal-rich component that closely follows the gas is the bona fide direct counterpart to the Magellanic Stream and was kind of stripped out at a similar time. And perhaps this metal-poor, more offset component was thrown out from the SMC during a previous interaction. That's just speculation that would kind of match this, but I'd like to see a simulation that actually reproduces that.
Can I comment on this? Well, someone can ask a question, but I have a comment.
Okay. Sort of related, I guess. Adrian Pricewell and Flatiron Institute. We have to do the front, the header. Anyway, this is going to sound overly pedantic, but typically when we say stellar stream, we mean stars that have been tidally disrupted from a thing. Do you know that these stars were tidally pulled out, or were they formed from the gas in the stream? You might know we've found stars that were formed in the leading arm potentially. So it's not out of the question that maybe the ram pressure that pulled the gas stream out also then did something to cause the stars to form later on.
Yes, I think that's a fantastic point. I think especially the red stars, they're metal rich. Maybe they actually match the metallicity of the stream. Maybe they were formed there. Most people I've spoken to think that the trailing arm certainly today does not have high enough gas densities where star formation would be feasible. And so I go with the story that Gertina's model predicts that you will have stars kicked out from the disk of the LMC, for example, and from the halo of the SMC. So to me, that's the most plausible explanation. But I'd be curious if people could think of any tests, maybe ages or something like that, so we could actually tell those two scenarios apart.
Hi, Nithya Kalivailil, University of Virginia. I don't know if this is too detailed, but I think related to both of your points. One of the things that we found, Eugene mentioned, there's a fair amount of, I wouldn't say discrepancy, but there's sort of like 1 sigma differences in proper motions measured from various surveys. One thing that does not change amongst any of these observations is the proper motion in the north component. It's always above 0. And the only way that you can get the past orbit of the LMC to align with the gaseous stream in any Milky Way model, because it's not very far in the past, so actually the deviations from model to model don't matter that much, is if you have proper motion in north of 0. And nobody's measuring that. So I would say we generically predict that for a stripped stellar stream, there should be an offset from the H1 gas and the stars.
Got it.
But for stars that are maybe formed in the stream, maybe that's different. So I just thought I'd point that out.
Yeah, it's interesting. Thank you. Thanks a lot.
Okay, last but not least, Richard Brooks. We'll talk about streams in a second.
Yeah, so they started about I mean, that's my understanding.
The pointer.
That's right. I can just use this.
Richard is going to talk about stream actions and energies in the forming Milky Way halos. Take it away, Richard.
Okay, yeah, thank you very much. So this is the last one of today, I think. So one more to go, guys. Then Danny's assured me there's plenty of alcohol outside for everyone to drink. So yeah, I'm Richard. I'm a PhD student at UCL, but I'm also here as a pre-doc at the CCA until June. Oh, okay, it's playing. So yeah, we heard a lot about dynamic stuff today, which is great. But a lot of times people motivate these things from looking at things like galaxy clusters, so collisions, like dark matter collisions, very far away from the Milky Way. And so this is like a classic example of the bullet cluster, where you can see the dark matter has passed through it, as highlighted in blue. And then in the pink, you have the hot gas, so it's like trailing behind. And so this is an example of a dark matter collision that's going on very large scales, very far away. But fortunately, as we've seen over the course of the day, we don't have to look that far away to find a dark matter collider. And indeed, the clouds are actually a local collider, or a very local laboratory for us to look at dark matter collisions. And so that's with the Milky Way, its dark matter halo, and then the clouds, and particularly the LMC. And so, yeah, what effect has this had on the Milky Way? You've seen these plots probably 10 times over the course of the day, but we've seen effects like reflex motion, so the disk being pulled towards the past orbit of the LMC. And so this is in simulation, then confirmed in observation. And coming up is also the dynamical friction signature. So this is then sort of the redistribution of the dark matter that follows the path of the LMC, and also the collective response, so that on the other side of the halo, when the dark matter has been redistributed. Okay, and so all of these effects are quite global properties in the Milky Way, and due to the LMC colliding with it. And what do these things do to the substructure in the Milky Way? And so particularly are we talking about stellar streams? And so this is always a brilliant plot to show, but this is around a collection of around 100 stellar streams in the Milky Way in the Gal Streams catalog. And so thank you, Cecilia, for that. But I won't be talking about 100 streams today, so that's great news for a lot of us, particularly myself. But I'll be talking about just these parts shown here. So the potentials that we're talking about are the Milky Way halo and the LMC halo. But the streams that I'll consider are GD1. So this is a globular cluster stream. So that means it's quite low mass of around 10 to the 4 solar masses. And at present day, it's relatively far away from the LMC. Whereas the orphan Chenev stream, which is now 1 stream, previously 2 streams, is shown in these sort of purple and green points below. But this is a more massive system, so a dwarf galaxy progenitor that's then been tidally stripped and has formed a stellar stream in the Milky Way. And so this has a much closer recent passage with the LMC than GD1. Okay, and so we've heard a little bit about what streams can be used for. And so today I'm going to be talking about mainly setting global Milky Way properties, so things like acceleration fields, or in particular the mass enclosed profile of the Milky Way. Whereas you can also use it for the substructure. So we had a couple of talks on this, but I won't be covering that today, although it's very cool stuff. Okay, And so the LMC itself has seemed to have quite a large impact on streams. And so this is taking the proper motions of streams and showing how the vectors are being misaligned towards the pass orbit of the LMC itself. And so it's sort of dragging the on-sky velocities to where the LMC is in the sky. And so this is one way you can look at streams, this sort of space. But I did promise these scary action variables, and so I'm going to have to talk about them. And so to try and cover this in one slide is a bit of a beast, but I'll give it a go. Anyway, so you start with your normal phase space, so 60 positions of velocities, and then you have to make some assumptions about the gravitational potential of the Milky Way, but then you are essentially doing a coordinate transform from phase space to action space. And when you're in action space, you have these three actions, which are the spherical actions. You can also have axisymmetric actions, but in this talk, I'll be considering spherical actions. And so when you've made the change to action space, your actions are then able to be integrated. So you're integrating an orbit of a star by just linearly increasing the angles. But thankfully, we don't have to worry too much about this. I'm not going to be integrating streams that we see today in action space. I will be doing it still in phase space. And so the key thing you need to know about the action modeling is that for a stellar stream that's forming in the Milky Way, because its progenitor is tightly disrupted, then they should all have very similar actions along the stream. And so they'll have some mean value that is then has some width based on internal properties of that progenitor, for example. And so stream actions, if the potential in which the stream is formed is static or is very slowly varying, so is adiabatic, then we can use this to then try and set global constraints on the Milky Way. And so this is done by maximally clustering the stream actions. Okay, and so this is an example of doing this. And so setting a mass profile constraint using streams and this action clustering technique. But often this is, again, assumed static Milky Way models, which we've seen evidence that this is, they're deforming, the Milky Way potential is deforming. They often haven't included an LMC and the other thing is that sometimes they're parametric models. So you're making extrapolations where you don't necessarily have the data to back that up. And so that's something that can be addressed. Okay, so then the key thing that we sort of want to answer was then how do the deformations to the Milky Way halo affect the action clustering of stellar streams? And so are these deformations adiabatic? Are they non-adiabatic? And in which case, are we still able to use these techniques to set constraints on the mass profile? Okay, so we've seen some nice examples of being able to simulate a deforming system. And so this is just taking Sophia Lenningen and Mike Peterson's simulations and showing the LMC falling in and the redistribution of dark matter. And so this is the density plotted here. And so you can see as the LMC falls in, the deformations are being tracked by using a basis function expansion. And so depending how you weigh the basis functions by these time-dependent coefficients, we'll be able to track through time the deformations to the halo. And so you can also look at this thing in the potential related through Poisson's equation. And so you can see the same thing here, except in the left two panels. So I'm not showing the gravitational potential enhancement, so how much it's changed relative to the unperturbed case. And yeah, in the first two panels, I've decomposed the Milky Way halo in just two of its moments. So the dipole moment and then the quadrupole moment. And so you can see how they form as the LMC is falling in on the black path. And then the two panels on the right are then sort of the fully live halos. And you can again see these deformations. And yeah, you should check these tutorials out and if you fancy using some deforming halos in your work. And so, yeah, we then can have a free rein to choose various subsets of deformations to these potentials, taking things out, excluding, say, the dipole, including the quadrupole, changing things up and generate streams. And so, as I said, we're generating GD1 and OC streams. And so this is just an example to show you by using a particle spray method, we can generate streams in various potentials. But what we're interested in is then the present day action distributions. And so what I'm showing you here is then the action distributions, the radial action distributions for streams generated in a fully deforming LMC potential, plus then a choice of Milky Way harmonics. And so the example here for the static monopole means that the Milky Way halo isn't changing, it's not responding to the LMC falling in, but there is always the live LMC there, okay? And so for GD1, this is taking, the final day position velocities and then calculating the radial action. And so you can see here that their action distributions look pretty Gaussian-like and pretty well clustered still, which is what you might expect if the potential had been fairly quiet or an adiabatically evolving. But when you look at the same thing for the OC stream, except in the case when the Milky Way halo isn't changing, so the static monopole, in all of the cases when there are deformations to the Milky Way halo, you see quite quickly that you can either have long tails to your action distribution or even bimodality, for example, when the dipole is introduced. And so this hints that with respect to the OC stream, then potentially the Milky Way has been deforming non-adiabatically, and we may not be able to use clustering methods to set constraints. But we can go and do this. And so now we're trying to find, based on those distributions, a set of coefficients that best describes the Milky Way to find its mass profile. So we take those distributions and we do some maximum likelihood estimation. And so what I'm showing you is the ratio of the acceleration predicted by these coefficients that we find normalized to the truth. And so for GD1, it's fairly quiet across where we have information. But for OC, as soon as you turn on these deformations again, we're having wild fluctuations in the acceleration. And so you'll see this translates into the mass enclosed profile as well. And because I've used spherical actions, and a lot of this is spherically averaging things, which I admit is probably one of the downfalls of this work, but you can then actually infer the mass profile by just rearranging this equation here. And so, I should say these are just like the maximum likelihood coefficients, and we have no uncertainties here. And so to do that, we use a Fisher information approach, but I won't talk about that, but that's where the uncertainties come from. Okay, and so just as a final couple of slides, this is the action clustering results. So for GD1, the truth in the simulation is the thick black line, and our recovered one is the dashed line, again with the confidence intervals of 1 and 2 sigma. And you can see that it does a pretty good job locally to recover the mass profile. Whereas this is certainly not the case for OC. And you can see that only in that case where the Milky Way halo wasn't changing, are you able to still use these classical dynamical methods to recover the mass profile. Now I did promise the energies, and so I'll very quickly flash them up. And so you can see they do a similar job, but you might naively expect energies meant to be worse because they don't care about the time dependence generally. If it's adiabatic, it's not adiabatic, they'll all be affected and they're not going to be like constants of motion like the actions are. And so interesting though, in this case for OC, the constraints don't seem to be as wildly affected. So I'll just show you that one more time. So that's kind of an interesting takeaway. And so I'll leave the summary up here. But I'm very happy to take questions afterwards, or I'm here for a very long time until the end of June. So please send me an email. So thank you very much and enjoy that beer after this.
Thank you very much, Richard. Questions for Richard?
Sorry for delaying the party, but I have a question, yes. What is most important here? Is it the proximity of the stream to the LMC or the length of the stream which determines the spread in angles and therefore the spread in actions?
Yeah. So I think they're probably both quite important. In terms of the length of the stream, one way you could try and look at this would be to split up the stream sort of along that its radial extent and do the same clustering method, but in bins along the stream, and whether that you see differences there. And then in proximity, I think absolutely, if things are close to the LMC, they'll be more perturbed dynamically. And so, I would expect these things to break down faster. So you could generate for example, what we're doing now, populations of streams, and look at these things. So that would be statistically quite a nice way to look at it.
Question, yeah.
Thanks for the really nice talk. For the energy clustering, do you have any like intuition for why that appears more stable than actions?
Short answer. I'm not sure. So there's a couple of things that can go on here. So there's two tails to a stream. So it's quite possible that when we're finding the maximum likelihood coefficients, we're just finding one of the two tails. And so we're finding almost like half the information that's there. So it's not telling you the full story. So maybe we're lucky and we pick the tail that's less affected, for example. But yeah, I think that's still something that we go towards in the future because, yeah, if you look at this, it would excite you for like using this not in just our galaxy, but external galaxies. If you have, 60 phase space, then this would be a really nice way to set like mass constraints on other galaxies. But yeah, for future work for now, Jake, yeah.
Let's thank Richard one more time.